We started with the one DOF system. So how to constrain one DOF, or here very fundamentally is constraining one translation. And we have been talking about ballpoint contact. So a spherical ball with the flat. So this is very fundamental. And from here, we talk about constraint lines. And that's how we proceed in this course. And particularly when we design something based on constraint principles, I think it's very important to identify these contacts and also the constraint lines. And that will lead you to further analysis and whether you can say whether it's exact constraint design, whether it's under constraint. So if it's under constraint, then there might be some degrees of freedom left, and it should be able to move in those directions. But before you can do that, it's very important to identify these points. So either the contact point and then the constraint lines. So they are very basics. So in this case, just normal to the surface will be the constraint line passing through the point of contact. So that's how you constrain one translation. If you extend the constraint line concept, what you realize that a simple pin, or what we call it a truss member with the articulating joint. Articulating joint means it's free to rotate at the ends. So it's just a truss member, and because it can rotate and although at the joints, what you realize that the connecting body, which is orange here, orange body with respect to the frame, it's a constraint along the longitudinal direction, along the direction of the truss member. So if you have the joints, then you can define the constraint line. So here also, I think what is important is if it's not a point, then what is the constraint line? And along the longitudinal direction, the stiffness is much higher because of its material. So it's EA by L. Longitudinal stiffness you are talking about, axial stiffness, is much higher than other stiffnesses. And of course, when we clamp it, so suppose when we remove the articulating joints and we rigidly fix it, rigidly clamp to the body, then what we what we understand that this member, so it's no more a member, then it's like a beam element. So a beam element and uniaxial, right? So it's a slender rod, and which can bend and can get twisted. So what you realize in this case, again the axial stiffness, the longitudinal stiffness is EA by L, which is much higher than the bending stiffness and the torsional stiffness of this wire. So in that case, we call it wire flexures. So normal terminology in this core in compliant mechanisms is called wire flexure, but it's nothing but a cantilever, kind of cantilever with a circular cross section, or it can be a prismatic one also with a square cross section, right? Or if it's a rectangular, then it will have a different stiffnesses in different direction. But okay, for the time being, we just talk about the circular cross section. So this is how you can constrain one translation. There are other ways you can get it, and one is last time I mentioned about folded leaf spring or folded sheet flexures. Sometimes people also call it a blade. So it's a thin sheet material. So it's again spring steel, you can say, any material which has a very high elasticity, Young's modulus. So here is a folded. So there is a sharp bend, and that's the requirement. It works only if the bend is very sharp. If it's gradual, it may not work. So in this case, if it's a sharp, it's a folded, then you will also get one translation constraint along the fold line, along the folding line. Very important to remember, and we will come to that. Similarly, if we arrange a flexure, so or leaf spring we call it, so it's not folded but sets. They are like symmetric in design, so it can be like two seats you can think of, right? So one is this and then the other is as normal, right? So what you do, this one you put in the middle and this one you separate it, half you put here and half you put on this side, and that's how you can get the seat design. But what you will get is when at the middle, when they when you assemble them, what you realize is the intersection, two plane intersects, and that intersection line is is the constraint line, is the direction along which these two body will be constrained. So this is also implementation, and that's how you can constrain one translation. But you realize that compared to just kind of this a truss member or wire flexures, the sheet, this sheet flexures, so this is folded and this is a straight one, right? Folded sheet flexure. So here you have larger area available to you. So many times the clamping is easier. The assembly is is simpler compared to this wire flexure. That's why many times it's preferred. At the same time, it has a wider area, and then the load capacity, the buckling load, everything will be improved. So in the case of folded sheet flexure, what you realize that when you apply force elsewhere, not along the fold line, what happens is one of these member, one of uh, the sheet flexures, the folded one will get distorted because the force is applied somewhere else. It's not lying in the plane. So if it's on the plane, it's a very steep. So for instance, it's very easy to demonstrate. If you take a kind of any visiting card with you, so for instance this one if you take, or any small piece of paper if you take, what happens is if you take this small, it looks very simple and looks very fragile, but what you have to understand is you just try yourself and you will find that there are 3 degrees of freedom and 3 directions are constrained, and that those are basically the motion in the plane that is constrained. So suppose if you simply pull along this direction, it's a very high, you cannot tear it just like that. So you can apply any large force, you cannot tear it, it's a very high. Same with in this direction. So if you clamp it in, if you just pull it, you cannot do unless it gets warped. So warp ho jayega and then only you will be able to pull. But before that you cannot any deformation. Same way, suppose if you want to place something and apply a moment which tries to distort this thing in plane, again you cannot do. So these three directions are constrained, but rest other directions is very easy, so you can get those deformations. So although it looks a very simple component, but if it's used uh, and designed properly, you can design very nice mechanism out of it. So this is one example. If it's a folded along the fold line, you get a very high stiffness, and it gets constrained along that line. So what do you see if you are applying force here? This force, so this will try to rotate this part, right? So it will get twisted, but this force will not deform this part because it's along the plane, so it's very stiff. Similarly, if you apply this force, so again this is along that plane, nothing will happen, it's a very stiff, but this one will get again twisted, right? Similarly, if you apply this force, again both will deform, both can deform, and that's why equivalently you get this rotation at this axis. But what happens if you apply a force along the fold line? So for instance, in this case, so what happens in this case, if it is very counterintuitive, but you can write equations, bending equations, using your simple theory, and what you realize that there will be no deformation. One way to look at it is it's lying on the plane. So any force component you resolve, and if you're applying force at this point along the fold line, if it's passing along the fold line, it's lying on this plane and it's lying on this plane, and along the plane these two sheets. So you can assume that there are two sheets and connected in series, so they are stiff, and that's why you get a very high stiffness along this direction, and that's the region you get constraint along this line. So this configuration will give you a very good constraint, translation constraint. So what it says that it constrains the body's translation along the folding line. That's very important. You should remember it constrains along the folding line. What is good about this is compared to any suppose if you take this member and you take this member. So this, if I have to make, I can say it is like this. So it's a fold line, right? But this point, so suppose I have an object here, some object mounted, and then it's connected at this point with some surface, right? What happens? This is equivalent to this, but what is good thing is this is floating. It's a floating line. So as it deforms, so suppose if it's like this, and if you apply this force, it deforms, right? But then you also get little kind of shortening, parasitic motion in the actual direction. But in this case, you don't get that. So it's free of shortening effect. We call it shortening effect. So, and it's mainly because of this floating line constraint. So, means I haven't heard of this term, but the way I look at it is, it's like a floating line constraint. This is fixed line constraint, but this is floating line. And what you have to remember is the folding line. So it's a constraint along the folding line. And I showed this video yesterday, so you can again see a very good design. So you have okay, this, sorry, my drawing is going hard. So it's clamped on this side, and no, okay, this member, but this member is not rigidly fixed. What you can see is there is a gap here from the base. This is clamped to this side through this member here. So these designs you can see, to get a very sharp bend, what they have done is they use clamping plates, and you can see the little screws here. So with that you can also get, you don't have to bend it, but you just take two sheet flexures and then assemble it. But you can see a little clearance at the bottom, so that it's raised a little bit, and then at this end you connected a bar, a link here, and then you have a weight to balance it, so that you can adjust it and keep it floating. So see that if you apply a force along this direction, it's a stiff, but all other 5 are is degree of freedom. How it works? So suppose if you calculate try to calculate the stiffness along the fold line. So that you have to remember that folded sheet flexures, the constraint is always along the fold line, and if you want to calculate the stiffness, so this is the direction. So uh, generally we also call it bearing direction. So it will take all the loads, right? So flexures are sometimes also used as a bearing, small movement. So what you see is a floating, but there is no physical contact. And since there is no physical contact uh, and only elastic deformation, what happens is you are free from any kind of backlash or virtual backlash, which you get because of the friction between the surfaces, contacting surfaces. But anyway, that we'll discuss again. But suppose if you have to calculate the stiffness in this direction, so this is given by the applied load Fz and the corresponding with the deformation in that direction. And when you have to do that, what you will get, so you have to simply apply your bending theory, simple bending theory. There are 2 components. Right? And remember, you have also this inverse, because it's a 1 by. So the first one is because of the bending of the sheets. So when you apply the load, you will try to bend. Of course, that's the bend, the stiff direction, but it still is along the plane. It will to bend. So because of that bending, so it will be very high, but still it's because of the bending. So because E and I is also there. So E is the second moment of inertia. And this is because of shear. So because they are relatively short, so there will be component because of the shear also. So there will be some component, because of those 2 you will get the total stiffness, and two of them, right? So I think we can refer some papers and you can easily get this derivation done. Anyway, I think if we have some design calculation, we'll be directly using these equations. But you also need to understand is A and B, they are the length of the 2 sheets. A and B is the modulus, I is the moment inertia, and again A is the area of cross section of this part. So it will be very thin. So this is A. So suppose if T is the thickness, then and W is the weight, so area is only WQ, right? So you get a very high stiffness, but if you have to, so this is the stiffness along the stiff direction. You may have calculated the stiffness along the other 5 directions, right? Which is compliant direction. And if you take the ratio, this ratio will be much higher, and that's why relatively the deformation in this direction is much lower than deformation in the compliant direction for the same force. And that's why means flexures, in the flexures also we can call it is a constant embodiment. So for translation, I think there are various examples, right? So point contact, wire flexures, truss, you have folded flexures or sheet flexures in series, right? And then you see how it works. But when it comes to one rotation, there is no shortcut. There is no one member which can give you one rotational constraint, and you always have to go through a intermediate member. That's the limitation. An intermediate member you mainly need because one pair will give you the rotational constraint, but it will also constrain the translation. And with the next one, you try to constrain the same rotation so that the rotational constraint is passed to member, but at the same time, it removes that constraint. And therefore, you get only one rotational constraint. So if you arrange in this fashion, so you can use it as a building block for rotation constraint. But there can be equivalence. There are many arrangements. So, but the idea is you have to identify the parallels. So 1 and 2, two sets of parallel trusses, right? So what you see here is, although it looks very different, but essentially the same. So you see is one pair here and here, and the second is this and this in the same plane, but in orthogonal directions, right? So in the same plane where you want to constrain them, so they should lie in the same plane, but the two pairs, they will constrain or they will be arranged in the orthogonal manner, right? In the perpendicular direction. So one is in this fashion, the other will be in this fashion. So if you simply connect this and then you connect this, what you get is ultimately you get the rotational constraint for this. So you can see out of the plane it can easily move and rotate. So you will get all the other 5 degrees of freedom. A very good example is also your drafter, mini drafter. So these days we don't use it because we have all the CAD tools available. But mini drafter mechanism, if you see, it's a very good embodiment of one rotational constraint. And how it does is so here you see here you have rigid members or flexural members, but here it's just wires. You can see these are simply cables or wires. So what you realize is still cables can be also used very nicely to develop any kind of structure or mechanism, and it's a use these days in many of the mechanism because these lengths can be very big, right? Even the structural member in architecture you find them, or in robotics you find cable driven robots, right? Because the articulating joints or the links can be very far from motor, the base actuated motors. Actuators you can, base mounted actuators you can use, and through cables you can control them. But the way it's done, you also need to have many times a compressive member or link which takes the compressive load. The compressive member, and many times it's also used for preloading. So you may identify that there is a spring here. So it's mainly to provide preloading to the cables so that these cables are always in tension, and it works well when it's in tension. And then the way there is a link, so these are one pair and this is another pair. So they act like a two pair of links in a plane. So it's very similar to that. And one thing also here you have to realize that if it's perpendicular you can easily get. If it's not perpendicular it will still work, but you may have a combined motion that you have to also understand. Same is happening here. I think the with the folded leaf spring also, that angle shouldn't be a 90-degree all the time. It can be different from 90-degree and it still works, right? So that you can always calculate, and it works, right? So similarly, suppose if you want to get another variation, so in all these cases, what you realize, you want to have one rotational constraint, you have to always go via intermediate bodies. Here, if you see this case, let me just wipe it out. This example, in this example, what it says, you have this these links, right? But then it has to be connected through a torsionally stiff body. It should be torsionally stiff, and there should be a gap, right? Then only you should be able to just constrain the rotation only. So there can be various embodiments. So you can have a sheet flexures, so 2 sheet flexures, but in between you have to have this torsionally stiff body, torsionally rigid body. So what happens when you try to rotate? When you try to rotate this body with respect to this frame or the base, actually you provide a twisting moment torque at this axis, and if it's a torsionally stiff, it gives you that constraint, right? So I think the requirement in this case, this gap. So this gap is very important. If you don't have, you don't get this rotational degrees of freedom only, but it will get coupled with the planar stiffness also along the, because then it will converge to a sheet flexures, and if it's a sheet flexure, then there will be 3 constraints. So if you simply want to have a constraint along the rotational direction, you have to have this totally rigid body in between, sandwiched. You can also get it through a cabling also. So suppose if you have these members, and if you route the wire like this, and then another member, this side is basically for preloading, and at the end you have to provide this spring, so that you can provide the you can adjust it, and you can tune your preloading. So the amount of preloading you can change this one. So you can see it can move in this direction, but the rotational direction is very stiff. So these are some examples, and again, but what is the problem in this case is this intermediate. So you have to always remember that this intermediate body will give you some problems when you have with the dynamics. How? Of course, buckling is one issue. Another is, suppose these two members, 1 and 2, they are idle, but you give some protection to this intermediate body. You just tap it. It will start vibrating, right? And there is no way to control, because all these are elastic members. They are like springs. These are like springs. So when you just tap it, it will start vibrating. And suppose if it's in the system, if you have some frequency which is matching with your resonance frequency, then it will start vibrating vigorously and it may fail. Fatigue is one problem in this case also. Fatigue and buckling, I think, is a problem in times when you go for a compliant design or a flexure design. So that you have to be aware of, and you have to take care of that. They are completely different components, you can say, and which can be used to constrain one rotation also. So one of the example I show that one of the I designed for transferring the motion from a ball screw nut to translation stays. You need a rotational constraint, so that your nut ball screw can only move in the axis direction, ball screw direction, and there we use. So bellow so it's a coupling, but it's a bellow. So if you it's just a bellow. So it's a stiff in torsion, but other directions is a compliant. Embodiment is also coupling, but you can see it's a series. So you can see there is a slit. So you cut it, and then you just leave little connection here, and then alternately you'll do. So you will get zigzag kind of thing. And that will also give you, so from the top it looks like uh, this, right, it will look like this. So there is a connection in between, so it can bend, it can easily bend. Similarly, if you see from this side, you'll see this part. And because it's so thin, it will act as a hinge, so it can again rotate. And since it can rotate, and the other thing is this thickness is very small, so then it will act as a cantilever, so it can also flex, so you will also get that motion. But the torsionally is a very stiff, it works like a flexures. So what happens if you have to constrain more than one? So what you realize that, okay, so you can always start with the constraint lines, that's the concept. And then either you convert into wire flexure design or some other design, or even with the contacts you can remove those degree of freedom. So suppose if you have to constrain two translation, right? So these are the two direction you were talking about. Along that direction, you just have two trusses or wire flexure connected, right? So you constrain those two translations. You can easily see what happens if I want to move in this direction. You can move, because what happens, it can easily bend. Same is true with this one. It can, because it's a normal, right? So in the normal direction, it can easily bend. So you will get that deformation. And subsequently, if you are talking about the rotation, all the rotation will need some motion in the perpendicular direction, which is possible in this case, right? So these motions at this point and these motions at these points will be possible, and because of that, you'll get only constraint in along these two directions, transfer constraint, but rest four will be constrained. The flexure embodiment will be this leafy spring with the holes. So what happens here? So suppose we have this leafy spring. So what we say that is constraint along this direction is a constraint along this direction, right? Rotation is also constrained, but moment we take this, we make two holes and then a slit, right? So it's a removed. So the member is like, it's just like this, then like this, and like this, right? So we call it notch. So it can be equivalently, you can make it like this also. So again, what you see, you have at this point, it cannot move along, but rotation can be done because this section is thin now, and that's the reason, because of this design, you'll get only two constraints. The rotational constraint of a sheet flexure is removed in this case. So in this case is 1, 2, and this rotation. This rotation you get rid of by putting a whole hinges here. So you get, so these are the equivalents. This only thing what you have to realize is constraining at this point. In this case, is constraining the two translation at this point. If you take a frame somewhere else, the rotation somewhere or the translation somewhere will turn into rotation or translation, vice versa, right? So because if you talk about this point, this will lead to rotation because it will rotate from this point, right? So you can get two translation just by using leaf spring with hole hinges, and this you can use it here at the three locations, and then you will get what? 2 plus 2, 2 in series. So total 6 constraint. And although it looks very flimsy and very fragile way to connect, but once you connect, you will realize that it's a rigidly connected, and it will give a very good design, and it can support all the load, everything, without passing any moments, and therefore there will be no deformation getting transferred to the top plate. And that's why these kind of mounts are used in the very sensitive equipments or instruments. So that's why they are called kinematic mounts. In this case, what's the problem is, because you have reduced the section, the load carrying capacity is getting reduced, and then it's so easy to fail. So what you do is, then you reinforce. So you increase the thickness here. So you put an embodiment then, but you still put these hinges here. And just by doing this, you don't compromise with the degrees of freedom, but still you can increase the load bearing capacity considerably. So this robust embodiment or reinforcement we discuss later when we cover the flexure section, how is it useful. So I think one of the way is also like we can use these blocks, building blocks. So suppose if we need to constrain this translation and this rotation along the same axis. So for the translation, it's very easy, right? We get a wire flexure here, but for this translation in the orthogonal direction, we can put this building block for the translational rotational constraint, what we cover, and we can get this embodiment. So this is the translation and rotational constraint along the same line, same axis, right? Similarly, we can do, but if it's like perpendicular axis. So suppose this is the translation direction, but your rotation is rotational axis. The constraint, rotational constraint you want to apply, which and perpendicular to this axis, the translation constraint. Actually, you don't have to go by these building blocks, but just a pair of these, because one will constrain this translation. By putting the another one, they will constrain the rotation along the perpendicular direction. So if it's in the perpendicular direction, then you can have a very simple design, and just by using a pair of wire flexures. So many times you have to remember whether it's a same axis or perpendicular axis. If it's a perpendicular axis, it's much easier. What happens if it's you want to constrain two translation and one rotations, right? So in this case, suppose if you want to constrain two translation and one perpendicular direction rotation, right? So now you remember, like if you want to have that, you use a pair, right? So this translation constraint and this rotation by this pair, right? This 1 and 2 you will get from the previous example, right? From this example. So 1 and 2 will give you this translation and this rotational constraint. But suppose, so this is something like if I look from the front, this is like this, right? So it will constrain. So maybe use dotted lines or constrain this direction, and at the same time, this will also constrain this rotation, right? But what I want to have is I also want to have this constraint, right? So translation constraint. So what I can have is I can have this constraint along this also. So this is nice, but now we are claiming that this is as good as this. Why? So suppose if you want to you want to make a very compact design, what you can do is simply connect diagonally. So once we connect them diagonally, what happens if you want to move in this direction? It's not, the deformation is not, it can go along this direction, but if you want to have deformation in this direction, what you realize that it will try to compress or elongate, depending on what you are doing. So if you are doing this one, then it will elongate. But the stiffness is very high, A by L, right? So it's a stiffness direction. So it will also constrain this part. So moment you have this, is equivalent to the sheet flexures. Now you realize, right? And that's why many times we ask if we have the sheet flexures, right? What is the equivalent design? So equivalent design can be this or can be this also. So you can get rid of, and so if there are three constraints in a plane and one is in the orthogonal section, you can very much replace these three constraints with a single leaf spring. So what you realize that all three constraints you can get just using one leaf spring. So you call it leaf spring or sheet flexure. And that's why they are used in the design. They are robust, it's easy to clamp, and suppose if you have to clamp these three, it's a very difficult, although looks very simple in design, but getting the design done is very difficult. So sheet flexures are many times preferred. What happens if you have two rotations? So yes, you can use the building blocks. So for this rotation, orthogonal, right? So orthogonal is this one. So this corresponds to this. And if you have this rotation, this you constrain with this. So what you realize that the constraint, any constraint you want to put, you put the constraints, the whatever the elements, whatever the design you use, you have to use them in parallel. So constraints, parallel fashion. So similarly, you can go on, and then you will be able to design a different kind of designs, different kind of design for different degrees of freedom or different constraints. If you talk about another embodiment, so here you have two intermediate bodies, right? 1 and 2. But here in this case, what you have done, you designed differently, and then you got the same degrees of freedom constraint, but you go via only one link. And how you go? What you did is first you try to constrain. So there are 5 constraints. So it can move along this direction. This sand body or the green body, the intermediate body with respect to the base. If you see, there are 3 and 2. So along this axis, it can move. The translation it will have. Now you want to connect them further so that you get only these 2 constraints, and you get rid of other constraints, right? So you have only one translation and 5 constraints from here to here, 5 constraints. Ultimately, you want to go towards 2 constraint systems. So you remove other 3 constraints also. So other 3 constraints are in this case. So these 2 constraints are embedded in this design. So this rotation, I think you can cancel by these 2. And this should get propagated also to the top. So it's you can identify this pair, 1 and this pair. So you get 1. If you talk about this rotation, right? This rotation constant, I think this pair will do, this pair. So they will constrain here, and again, which are the other two pairs? We constrain that rotation, this pair, the next one. So they will constrain both. Now you have to release 3C from here to here. Which one? So this is there. So okay, it's a release. So if it's a released once, it will be released. So although with respect to the intermediate and orange body, this is constrained, but since this translation is not constrained below, so it will still move. What about the other motion? So this motion is released here in this mechanism. If you are talking about this motion is released here, right? So that you have to identify, and you can also use this approach. Moving serially and then eliminating constraint one by one. So the embodiment can be the simpler embodiment. So you know these three can be replaced by this, and these two in plane. Just two translation you can replace with the seat flexure with the hinge, with the whole hinge. So they will also give you the state guidance mechanism. So here also you have the same translation, and the top you will have the same configuration. So you can, so there are different ways. So for the same two rotational constraint, you have 1, 2, 3. You can have many more. So it depends on you. What happens if you want to constrain 3 translation? So of course, then along the 3 direction, you just put 3 wire flexures, and you can constrain the 3 translation, right? Again, these two are in one plane, so you can replace with this, and you can still get 3 translations. So it's a better. You have to manage 1 sheet flexure and 1 wire flexure. What happens, suppose if you want to constrain 3 translation, but which here it's lies on the body, but what happens if it doesn't lie on the body? So suppose if you have these 3 constraint, 3 wire flexures, what happens? They constrain the 3 translation, but what happens wherever they intersect? So suppose they are all the 3 intersect at point P, you will get the rotational degree of freedom at this point. So it constrains point P, all the 3 translation, but at the same time, you will have all the 3 rotation at this point. So in this case, can you visualize this? So actually this disk, green object will move on a sphere, on a spherical surface. So it's a part of a sphere here. So if whatever you see, it's a spherical surface. And the center will be at point P. So you will get remote center of motion. So suppose this is one disk or anything you want to manipulate at some remote point, you can still do by designing this way. So suppose if you are constraining 3 DOF here, and here you are constraining it in a plane. So it can move in X and Y, and it can rotate in plane theta, right? So perpendicular direction. So actually it moves in a XY plane. So right, X, Y, and it can rotate also, right? So you will get planar motion using three legs. But what happens if you have this 3 folded leaf springs? So all these legs, the constraining line, you can equivalently replace with these folded leaf springs. But you realize that this is very good design, because these are like 3 floating lines, 3 floating legs. And in this case, no matter where you move, you don't have any shortening effect. In the previous case, if it moves along x, y, there will be some shortening effect, right? So if there will be some shortening effect. Huh? So many times we call it parasitic movement, but in this case you don't have. And the one of the way to look at is I have one design made here. So what you can see is three folded leaf structure, and then what you can see is I move very nicely. I can rotate it also. But the thing is, if I apply a force, apply a load here, it's a very stiff. So although it's made of plastics with a 3D printing, still you can see the strength is very high. So imagine if you make it out of leaf springs with the spring steel, it will be very nice. So this is one of the example, and I will show the video later. And again here you see 3 leaf springs, right? So one leaf spring here, one leaf spring here, and one leaf spring here. And these are like 4 lines you have. So along the 4 lines, you can see it's a constraint. So one of the way to look at it is no matter where you apply the load, so moment and load, you will always have 3 forces, equivalent forces, balance these three lines or 3 legs, right? And that's the reason it can support load in the plane, right? So you can always define that. So suppose what you have to do if you have to constrain all the 3 rotations. So of course in the orthogonal direction you can have 1, 2, 3 of them, and you can then constrain 3 rotation, right? Likewise, you can start using, and then you can constrain 2 translation, 2 rotations. So I would like you to just try yourself and find it out how this. So you can level them 1, 2, 3, 4. These wire flexures 1, 2, 3, 4, and I ask you to deliberate how is working x. So suppose x, y, and z. So I'll ask you to just look at the translation and rotations along x, y, z, and x, y, z, and then tell me which one is doing what. How, if I ask whether the rotation along x is getting constant here, so of course it's not constant, but rotation along y is saying constant, right? Rotation y is getting constrained by 1 and 2, right? What about rotation z? If I want to rotate this, how is getting constrained? 3 and 4, because 3 and 4 a pair, they will not allow it to rotate, right? Why? How? Because if for the y direction is easy to see, so it's a pair, so they will not allow it to rotate. It's a constraint. So likewise, I will ask you to do different kind of thing. Again, it's in plane, so 2 and 4, 1 and 3, and then equivalently you can convert into this kind of sheet flexures embodiment. So equivalently you can get this kind of designs. Now what happens if you have free one DOF, only one DOF translation? So many times you also want to design a straight line guidance mechanism, right? So you want to only move in one direction. So this is one of the way 3-2 configuration, right? And only the third part is not here. So in this direction you don't have, so it's easy to move in this direction. Other way is just get this, right? And you can get a translation in this direction. So you can equivalently also make, so the back one gives you the 1, 2, 3 is equivalent to this shift flexures, and the front one, these two, will give you can be replaced with this, right? So you'll be able to explain vice versa. So suppose if you have, I ask you to deliberate on this design, you should be able to make this equivalent design with the wire flexure, and you will be able to explain how is constraining other 5 DOFs accept this translation, right? So similarly, you can do for the rotation. So suppose you only want to have this rotation. So I think you can start with, so many times you can start with 3-2-1 configuration, and you can start eliminating. So 3-2-1 means 3 from the bottom, 2 from one side, and 1 from the other side. So it constrains the body completely, and whichever direction you want to have, or whichever DOF you wanted to have, just remove the constraint accordingly. So by removing 1 or 2 wire flexure, you will be able to see how to get those degrees of freedom. So this kind of questions I may ask in the exam as well. There are other kind of members, flexural members, I would say, which also gives this kind of motion. So suppose if you want just one rotational degree of freedom, so this kind of open section can also give that degree of freedom. So it's open section, so it can twist easily, and you can get this degree of freedom. This will have some limitations because of shortening effects. So you design it diagonally. So this line is no more like this, but it's a diagonal, and then you'll be able to twist it. So one of the example is this leaf spring, putting leaf spring in cross, right? So what happens in this case is maybe. So how to visualize? So in this case, if you see from one end, it looks symmetric, and it just look across here, but it's like this. So from this side, if you see, this is the leaf spring, other side. So it's like and the other one is like maybe so it's something like this. So now I think hopefully you will be able to see them. So these are connected together with the rigid body, and these two ends are connected with one. So when you apply a movement, actually it can rotate along this line. This is the idea. So you get one rotation along this axis. So very simple one. So you try to visualize, or you can make a CAD and you can see it. So here also, I think there is only one rotational degree of freedom, and which is along this when the two plane intersects. So center line leaf spring. So this is one of the way. You can get the symmetric design also. What you do is you split it, and then you move one to this side. So you'll have this kind of design. So half the width, then you have full width, and again half width. This is called symmetric design. And what we claim that the stiffness for this one is much higher, better, the load bearing capacity compared to this one. So we'll discuss later. But this is one of the way to get a rotational constraint. Many times people wonder, and then what they do is they connect them like this in single plane. So I think, so fuse them. But moment you do this, the stiffness is much higher compared to this one. So this you have to be aware. So once they are intersecting and merged, and when they are not, they are intersecting but they are separate. So the stiffness is very different. Of course, you can also design a kinematic mount. Kinematic mount means it's a kinematically mounted, fixed. So all 6 DOF constraint. So of course, you can do 3-to-1 configuration, and you can also use this kind of setup. So three C's here and 3 C's. So if you just constrain a point, it constrains all the 3 translations. So 3 translation at another point, and here you have 2 translation and 1 rotation. But they can constrain all 6. You can visualize that. You can illustrate by just writing X, Y, Z, and you can see how it does just by putting the lines, the constraint lines, right? X, Y, Z. And then you should be able to explain how it constrains the rotation and other parts, right? So equivalently, you can also see that these 3 is equivalent to this one, and these 3 equivalent to this one. So this also you can see the equivalence. But if you really want to have kinematic mount, you also go for 2C, 2C, 2C. And if we, of course, what you have to see is the plane. This plane is orthogonal. So one is like, if you see from the top, this is like this, 2 side, and this is like this. The plane is different. And then you very much you will be able to see how it works. So you will get the thermal center also here in this case. Now the question is, you have 3C here with the 1/6 flexion and 3C with this here. Do you think it can constrain all the 6 degrees of freedom, or whether it can provide you 6 constraint?